sticking around to the end. I know it's late in the day, so hopefully it doesn't vary too much. But this is going to be talking about a joint work with Philippe and two grad students here at MIT, Sinhao and Austin. So to motivate this, what I'm going to be talking about is data that's not in RD. Right? So this picture you may recognize from the previous talk, right, where I have shapes, and I want to maybe talk about how to interpolate between shapes, or generally, how do I calculate averages between things that just aren't data points in RD. Right? So if I were to take these two shapes and just take if I maybe had a uniform distribution on these two shapes in R2, and I took like an L2 average, you get something that looks like this, right? You just weigh each by a half, and I get something that looks kind of messy like this. This isn't really respecting maybe the geometry of these two shapes, and a more natural average might be something that looks like this, right? And this is what's coming from optimal transport, right? So optimal transport, I know we've seen a lot of it in the past 3 talks. It's becoming more and more popular, I think, in a lot of applied fields. You see it in machine learning, graphics, image processing, neuroimaging, economics, and of course there's many, many others. And this is not the focus of my talk, but just to say that there's this whole field of actually applying these tools to practical problems. And we saw this one, I think, the last night as well. This word with that word movement distances. Okay, so to motivate more of how we're going to be talking about averages, not in RD, we need to talk about the Wasserstein spaces. And so the Wasserstein P space is the metric space of probability measures equipped with this distance. Right, we've seen this distance before. It's basically the infimum over all couplings between 2 random variables x and y. And this is just saying that x has a marginal distribution mu, and y has a marginal distribution mu. Right, I want to minimize over all such couplings the expected distance between them raised to the power of p. And this defines the Wasserstein P distance. Okay, and this is a natural geometry for distributions over RD. Because, as I guess Santa Bures points out in his book, right, this is a horizontal distance rather than a vertical distance. Right, so here I've rewritten it in terms of the transport function, right, that we saw in John's talk as well, where under certain assumptions on your measures, right, instead of writing it as couplings, you can write it as minimizing the distance between x and where I transport x with some function t. And there shouldn't be a d here, of course. Right, but what I'm showing here is, let's say in R1 I have 2 densities, F0 and F1. If I were to do an L2 interpolation, I would get the purple dotted curves, right? You would basically just shrink this one down vertically and then push this one up vertically. On the other hand, if I look at the optimal transport or Wasserstein geodesic between them, I get something that pushes horizontally between the two. Right? And you see this, of course, in higher dimensions as well, where I have 2 Gaussian distributions in R2, and there's a sort of smooth interpolation between the two. So the goal of this work, or the, I guess, overarching goal of what I want to talk about is, can we actually efficiently compute the center of a distribution over measures using first-order methods, meaning gradient methods, right? And so this is really a talk about giving computational rates to algorithms for computing averages on the Wasserstein space. And specifically, when I talk about efficient methods, what I want to prove, as somewhat an optimization, is something like maybe linear convergence of gradient descent, or a fast or parametric rate for stochastic gradient descent, right? That meaning like a 1 over n sort of rate. So it's the outline of what I'll talk about. First, I'll just review some stuff about optimal transport and barycenters. And then we're going to restrict to the Bures-Wasserstein Manifold, right? And we're going to restrict to this case because the general space is very hard to work with, but we can actually get some results in this sort of subset of Wasserstein space. I'll take a quick detour through geodesically convex optimization and show you what the results there would give you if you tried to apply them to this case. And then finally, I'll finish up with the rates that we actually get for this manifold, or computing barycenters on this manifold. Okay, so optimal transport and barycenters. So to understand the averages that you actually get in Wasserstein space, we need to be able to talk about how to actually interpolate between distributions in this space. So for the rest of the talk, we'll be focusing on the 2-Wasserstein distance, right, which is just the distance to the power 2 inside the expectation, right, and then to the 1/2, of course. And to go between the distribution mu and the distribution nu, right, the points along this curve are given by this displacement interpolation, where every point along this curve has distribution given by the law of 1 minus t times the random variable that has marginal mu, plus t times y, which has marginal distribution nu, right? And I'm assuming here that these x and y's are actually optimally coupled, right? So they actually achieve this infimum here, right? And this is actually how you end up finding the geodesics on this Wasserstein space. Now, under some maybe regularity assumptions on the measures, instead of talking about couplings, I can actually talk about transport maps. And here what you see is I can write this distance only in terms of the initial measure mu, and I'm minimizing the distance that x has to travel so that the end distribution after pushing forward is nu. Okay, so this is maybe a more useful way of actually thinking about what's happening is I'm pushing points forward from the measure mu to the measure nu. Okay, so Wasserstein Barycenters, basically, given this sort of geometry that I've discussed, is what we want to do is we want to minimize the squared distance between a point on Wasserstein space, right, the distance between B, and say the average over all points in the distribution P squared. So here I have a distribution over measures. So P is in P2 of P2, right, where this is Wasserstein space. And the Barycenter is defined as any minimizer of this sort of integrated squared functional, which I'll define by f of b. In the discrete case, you can think about finding a Barycenter of the discrete things, of course, where you have maybe a weighted sum of Diracs, and I'd want to be able to find a Barycenter of this discrete measure over Wasserstein space. And this might be actually what you try to solve in practice. Now, some stuff is known about these Barycenters. So let's say that I sample n measures from this continuous distribution P up here. Under some regularity assumptions on, say, the mu's, I can get uniqueness. We get consistency. So as n goes to infinity, I get convergence in Wasserstein distance of Bn with this true Barycenter B bar. However, if I want sort of guarantees on finite sample sizes, at worst, you see you have this n to the minus 1 over d type factor, which is what you saw in John's talk, right? So even estimating Wasserstein distances is hard. As we see, the estimation of a Barycenter over Wasserstein space is also hard. However, recently, under additional assumptions on, I guess, more regularity on this P distribution now, you can get better rates of convergence. Right? So we can actually show that the empirical Barycenter converges to the true Barycenter with a parametric rate, right? A 1 over n type rate. And this holds, for example, with Gaussian distributions, which will be the case that we discuss more in depth later on. Okay. I just want to highlight quickly that this is related, these sort of rates that we want to get are related to estimating the mean on a Hilbert space, what we really want. Right? So if you think about, I have random variables that are distributed P. They have mean mu and variance sigma squared. Your short calculation tells you that the sample mean achieves an error with the true mean that's on the order, or that actually equals sigma squared over n. Right? And these are the bounds we'd really like to show for the Wasserstein case. And that's actually what was shown in sort of this most recent work on empirical Barycenters. But you notice in this Hilbert space, I have a closed form expression for the mean, right? I just calculate the sample mean, which is the sum of the xi's over n. But in Wasserstein space, I can't just add my measures, right? That would be the sort of L2 mean, which, as we saw, isn't really respecting this horizontal geometry. So in practice, we don't actually know this empirical Barycenter. We have to find it. Now, the nice thing in the Hilbert case is you see that this function that you're trying to actually optimize is one strongly convex and one smooth, right, just by sort of our definitions. And so it's really easy to optimize, right? So if you run gradient descent or stochastic gradient descent, you get really nice rates.
right? So can we get something like this on Wasserstein space? Despite the fact we can't just come up with the closed form expression for the sample mean, can we prove maybe something like this to get fast rates of convergence for gradient descent and stochastic gradient descent? OK, and to make matters sort of more simple for us, we're going to restrict to a subset of Wasserstein space that's a bit easier to deal with. And this is the Bures-Wasserstein Manifold. So first of all, this is essentially the restriction of the Wasserstein distance, or the Wasserstein space, to just Gaussian measures. So gamma, m, sigma is going to be the Gaussian distribution with mean m and covariance matrix sigma. And it's pretty easy after you've maybe read some of the books on optimal transport to figure out what the transport map is. Right? This is you can verify that this, under a change of variables, actually gives you the correct distribution if you plug in x distributed with the initial measure. Right? So you actually get the correct distribution out. And the other characterization you get for optimal transport maps is that they're gradients of convex functions. Right? And if you basically interproduct this with x and put another x minus m naught on this side, transpose, you can see that this is actually the gradient of a convex function. OK, and so with this, you can write down your formula for the Wasserstein distance over Gaussian measures, and it's just given by this formula, right? So I have the distance between the means and some term involving the covariance matrices of the initial measure and the measure that I'm transporting to. And you see, this is kind of nice. The mean and covariance terms separate, right? So I can think about transporting with respect to the mean separately from with respect to the covariance matrices. And this is exactly what you, I wanted to talk about this first. One of the nice things about this set, and this is one of the, say, simplest cases of this in Wasserstein space, and the reason we deal with it, is it forms a geodesically convex subset. So between any two Gaussian measures, if you interpolate between them using that displacement interpolation I talked about earlier, you're going to only get Gaussian measures, right? And this is nice then for optimization. Like, we're not going to step, if we move on terms of transport maps, we're not going to step outside of this space. So we can maybe come up with some nice algorithms just restricted to this space. So because the mean and covariance separate, we're just going to restrict to mean zero Gaussian measures. Because transporting by the mean, you're just transporting the whole distribution by that fixed distance between m0 and m1. And so you're left over with just this as your transport map between the two. And this is your transport distance. Now, with this distance metric, you can then go to Riemannian geometry and see what sort of manifold you get. And so on covariance matrices, I guess positive definite covariance matrices, this induces a Riemannian structure that's non-negatively curved. Right? This is in contrast to maybe the familiar Riemannian structure that you encounter on positive definite matrices, where you use this sort of, there's this other metric, right, with the log Frobenius norm or something that induces a non-positively curved manifold. And if you're interested, there's a variational form of this Bures-Wasserstein distance, which I'm denoting by d of bw now because it's operating on these matrices. And it's given by this. Basically, I take my two covariance matrices, I square root them, and then I have to find the optimal rotation that minimizes this Frobenius norm distance between the two square roots.
Is there a way we should think about that geometrically?
What do you mean? Like, I'm not sure. It's more just, it's just, I guess the only thing I'm thinking is that you find the optimal rotation between the matrix square roots. But it's sort of aligning in some sense. It's a bit hard to think about because you're only aligning sort of half the right eigenspace in some sense, right? So it's kind of hard to maybe think about what geometrically this means.
So what exactly are we optimizing of? So is it all unitary matrices or?
Yes, or yeah. So if we go to, if you want to think about some special cases of this, you can compute it in one dimension, and you get a nice distance between the variances. It's just the difference between standard deviations squared. If you think about diagonal matrices filled with positive entries, this sort of looks like a Hellinger distance, at least when the sum of the p's and the sum of the q's are both 1. And this is actually also encountered in quantum information theory, where you have the trace of the matrices equals 1, right? This extra term that comes out is actually normally referred to as the fidelity. And so this has connections to a lot of stuff in quantum information theory that I don't know so well, but I guess this was first considered by Bures back in '69, and that's sort of why we call this the Bures-Wasserstein space. So I can then translate my ideas about Wasserstein barycenters. Since this is a geodesically convex subset of Wasserstein space, let's just try to find a barycenter of these positive definite covariance matrices. So if I translate what I wrote before into this formulation, I get that I want to find a covariance matrix that minimizes this integrated distance squared with the sort of whatever is distributed according to P, which is my distribution now over the Bures manifold. Okay, and you can actually write down explicitly what the form of these equations are, right? You get that the thing you want to minimize for the continuous case is just the integral of this trace, and in the empirical case, it's the sum of these. Right, and this is a non-convex program, so we maybe don't know how exactly to solve it. But we can try, right? So we can differentiate this. And we can actually differentiate the barycenter functional on the more general Wasserstein space. And in a really nice sort of compact form, you can say that the gradient of the barycenter functional is just the average of transport maps, sort of where you're averaging over your measure P. So if I'm sitting at some measure B, and I want to calculate what is my sort of gradient, or what is my sort of the differential of my function at my current point, it's really just given by looking at the transport map with all samples, or sort of all things that are distributed according to P, right? So in the empirical case, right, again, the integral just becomes a sum. Right, and then you can do gradient descent with this, right? This average of transport maps actually gives you a transport map back. So you can think about doing this, right? So I differentiated the barycenter functional. I can do gradient descent or stochastic gradient descent. Gradient descent just takes the form where I basically move in the direction of this minus gradient, right? And I push my current measure bt sort of in this direction given by the minus gradient. And I move maybe some distance, and I get out bt plus 1. In the stochastic gradient descent case, I'm sampling maybe mu t's distributed according to my distribution P. And at each iteration, I'm pushing towards this new mu t with some step size a to t. Right? So I'm pushing along the geodesic to get my next estimate, bt plus 1. In the Bures case, these have exactly written formulas, right? And this formula is a fixed point algorithm that was, I guess, originally given by Alvarez-Esteban et al. In 2016, right? And this is actually just essentially doing gradient descent with a step size of eta equals 1 here. The stochastic gradient descent, you're just pushing forward, again, this covariance matrix along the gradient, and you get something that looks like this. But you don't need to worry too much about the forms, just that we can write them down, and it's all just matrix multiplications. So before our current work, people observed that there's numerical linear convergence of this scheme, right, this sort of fixed point iteration. And they only were able to show asymptotic convergence of this gradient descent method. Later, for the stochastic gradient method, Backhoff-Bourgois et al. Showed asymptotic guarantees for SGD, but again, no rates. Right? So really what we wanted, it was a a non-asymptotic rate of convergence for these methods. So I'm going to take you through a quick detour through geodesically convex optimization because you can actually get some rates for estimating the Bures-Wasserstein Barycenter using these results, but they're not very satisfying. So what is a geodesically convex function? A geodesically convex function is just a function that is convex along geodesics, right, as you'd expect. So if I have some space, and I have a geodesic in this space given by gamma of t, then it's geodesically convex if for any geodesic, f evaluated at a point along the geodesic is less than or equal to, right, t times f at the endpoint at 1 plus 1 minus t f at the endpoint at 0, right? So it's just the standard convexity thing, but along a geodesic. Now, if you're doing this on a Riemannian manifold, and you can actually differentiate your function, this becomes equivalent to the normal thing you'd see with sort of Euclidean optimization, where you say that f of y is greater than sort of the linear approximation at x. And so what do I mean by these things? Well, this, in Riemannian terms, right, we have a Riemannian metric that induces an inner product on the tangent space at x. And this gradient is actually a Riemannian gradient, which is basically just the element of the tangent space that actually gives you the correct directional derivatives, right? But you don't need to worry too much about it. Just know that this just looks like the sort of Euclidean form of the convexity assumption people normally make for a differentiable function. And then you can equivalently think about alpha strong convexity, where now you just add on alpha over 2 times the squared distance, right? So this is what I mean by sort of a geodesically convex function, and this is what I mean by an alpha strongly geodesically convex function. So using these sort of assumptions, you can get some standard results from convex optimization. For example, if I assume that my function is strongly convex and smooth, where smoothness is sort of in a manifold sense, I don't want to get into that, you can get this sort of linear convergence rate for gradient descent on the manifold. On the other hand, for stochastic gradient descent, you can get the same sort of result you get in Euclidean space, again, where if you have strongly convex plus smooth, you get this parametric rate of convergence. And there's many other works on geodesically convex optimization that I'm not going to touch on today, just because these are the two sort of algorithms we're concerned with in our work. Now, one of the annoying things here, right, is of course these results depend on the curvature of the manifold. And especially it's hard to sort of think about what's happening when the manifold is non-negatively curved, like the Wasserstein space. And something that I really want to hammer home here is that this space that I've created on positive definite matrices is not geodesically convex. It does not give you a geodesically convex distance squared. So here I'm plotting the Bures distance between a matrix C and some other geodesic on Bures space. And as you can see, this is the distance squared between my point C and points along the geodesic, right? And this is very non-convex. Interestingly enough, this distance squared actually is convex along Euclidean geodesics, where if I just interpolate linearly between these two positive definite matrices, I get a positive definite matrix. And actually, this function is convex along that. But we can't actually utilize that in these gradient descent algorithms that we want to think about. OK, so back to the Barycenter problem. We have these sort of general results from sort of analysis on manifolds. This one goes back to Curvature in 1977, which basically tell me when this Barycenter functional is strongly geodesically convex on a manifold. If the sectional curvature of my manifold is sort of non-positive, then I know that my Barycenter functional is strongly geodesically convex sort of globally, right? So this is the really nice case. But this is not the case for Wasserstein space or the Bures-Wasserstein manifold, where things are non-negatively curved. So if the sectional curvature M is bounded above by some positive constant C, then I need to assume some more things. I need to assume that these x's, my points on the manifold, sorry, these should be xi's here instead of p, that these xi's lie in some open convex ball of radius rho, then I know that g of m is strongly geodesically convex in this ball only if the radius of this ball is sufficiently small, where the radius really depends on sort of how large this curvature upper bound actually is. So the more highly curved my manifold is, the smaller I need to restrict my attention for this function to be strongly geodesically convex. OK, but if I just sort of just go back to using these results from geodesically convex optimization, at least if it's strongly geodesically convex, I could get linear convergence of gradient descent and a parametric rate for stochastic gradient descent just by sort of using these results for first order methods on manifolds. Now, if I wanted to think about what sort of bound am I actually getting here, what sort of restrictions am I making on the sort of support of my distribution to satisfy this curvature bound, I need to think about like what is the curvature bound of Wasserstein space. And so I'm just given a bunch of different spaces, right, for you to sort of think about that these are non-positively curved spaces, these are flat spaces, and these are non-negatively curved spaces. And really we're sitting here. We're a subset of Wasserstein space that's sort of non-negatively curved. All right, so you can sort of think of this as maybe we're on like a sphere of some kind. And a recent result gave this really nice bound for what the sort of an upper bound on the sectional curvature of the Bures-Wasserstein manifold at a point sigma. And this upper bound is given by the following. It's given by 3 over the sum of the bottom 2 eigenvalues of sigma. Now the result they give is actually more general. They prove it for the fixed rank Bures-Wasserstein manifold, where you're dealing with matrices that are not positive definite, but rather positive semi-definite with a fixed rank. But for our case, this is the bound that suffices. And really what you're saying is that as you sort of make these eigenvalues smaller, or as you approach the boundary of this positive definite cone, right, the curvature grows. OK, so, but we can actually use this, right? We could use this to give you a result from geodesically convex optimization that would give us these convergence rates for stochastic gradient descent and gradient descent. We know, I'm not going to show you, that the distance squared function is smooth. The curvature is bounded above by k as long as we don't approach the boundary of the positive definite cone. And if we assume that our observations and iterates lie in some ball, then we get convergence. Now the issues with this, right, are of course this can be super local, especially if my curvature, my ball is chosen to be close to the boundary. But even outside of this, I haven't guaranteed that this actually happens. I haven't guaranteed that my iterates actually remain in this ball. And this actually becomes a pretty non-trivial task, is actually guaranteeing where the gradient descent and stochastic gradient descent iterates actually go. OK, so we don't have guarantees yet. And this is where we had to look to other inspiration to try to find how to get some guarantees for gradient descent and stochastic gradient descent for Bures-Wasserstein Barycenters. And since this is a non-convex problem, we of course, looked to the non-convex optimization literature. Right, and one of the things that people do a lot there is you take some proof from convex optimization and just alter some assumptions, right? And then you are sort of in a non-convex case, but you have exactly what you need to still succeed. So one of the most common ones of these is to assume a Polyak-Woyashevich inequality, or a PL inequality, which basically tells me that my gradient squared grows by some constant factor times the function values. OK? And this is actually some sort of proxy for strongly convex, sort of the strongly convex assumption that you would need in convex optimization. And so if I use this PL inequality and smoothness, then it's pretty easy to show that you get a linear rate of convergence for gradient descent and the parametric rate for SGD. Right? And this does not imply that my function is convex. It implies something more general called invexity. OK, but so if we are able to prove this PL inequality, then we actually get a result. And I'm going to show you the result that we actually get now, because the spoiler is we actually do get a PL inequality on the Bures-Wasserstein manifold. So the assumption that we make is given at the top. Basically, for some parameter zeta that's fixed between 0 and 1, I assume that the support of my distribution lies in this set S zeta, which is positive definite matrices whose operator norm is bounded above by 1, and whose determinant is greater than or equal to zeta. You can, of course, rescale things to get operator norms bigger than 1, but this is just for the simplicity of presentation. And if this is the case, if the support of my distribution is contained within this set, then this P has a unique barycenter, and I get the rates of convergence that I want for gradient descent and stochastic gradient descent. That is, I get a linear rate whose rate depends on this parameter zeta, but it's still linear. And for the stochastic gradient method, I get something that looks like the variance over n, right, which is exactly analogous to that rate that you saw on Euclidean or Hilbert space, right, but in a non-convex setting. So the key steps to getting this result are that we first show that gradient descent and stochastic gradient descent actually remain in this geodesically convex set. Right? And to do that, we employ some results from the Barycenter literature that involve talking about functionals that are convex along generalized geodesics. But to avoid defining a lot of extra things, I'm not going to go into that. But we're able to prove also smoothness and a PL inequality, which yields convergence of this function, or sorry, this sequence, which is the difference in function values from the optimum, like in the same way as in the Euclidean setting. Okay? And these proofs use this non-negative curvature of the Bures-Wasserstein manifold in a very sort of particular way. And finally, to move back from this to estimates on the distance, which I showed you in the previous slide, we prove a variance inequality, which is essentially saying quadratic growth, that this function grows as some constant factor, or sorry, is bigger than some constant factor times the squared distance with the optimum. Okay, so the only thing I'm going to show you the proof of, just for time, is how we get a PL inequality. And the PL inequality, very simply, is under our assumption, we get the following bound. We get that the difference in function value from sigma to the barycenter is less than or equal to this constant, which depends on this parameter zeta, times the gradient norm squared, where the norm is evaluated in L2 gamma of sigma. Okay, so maybe this norm looks a bit weird here. Why didn't I just take like a 2 norm or something? It turns out this is the exact correct norm that you use on the Bures-Wasserstein manifold. Right? It's the norm induced when you look at Wasserstein space. The tangent space in Wasserstein space is given by L2 spaces. And so really we're thinking of this gradient as a transport map, and we're integrating it in L2. OK, so let's think about the assumption first. Right? So as I said, we're in this subset of the positive definite cone. And if we think back to what the results on geodesic convexity would have needed, right, I have basically that I need to assume everything is happening in some very small ball, especially if I'm close to the boundary. On the other hand, really, there's no bounds on this set S zeta. Right? We just trade that off with our convergence rates. So really, we can come up with whatever set you want in this positive definite cone, as long as we don't actually touch the boundary. So to prove the PL inequality, we need a few steps. The first of which is proving regularity of transport maps. So I showed you that earlier, this is the equation we used, or that's derived for the transport map between the normal distribution with covariance sigma naught and the normal distribution with covariance sigma 1. And for sigma naught and sigma 1 in this set S zeta, you can essentially show that the eigenvalues of the gradient of this transport map are bounded below and above by some quantities that involve this zeta. Right? And this ensures some sort of regularity about the transport map. Basically, it's strongly convex, and it's smooth, right, with some parameter that depends on zeta. The other tool we need is a variance inequality, which I mentioned at sort of the end of one of the slides. And basically, we get a variance inequality with parameter zeta from this regularity. The third tool that we use is we actually develop a more general sort of integrated PL inequality that sort of gives you the skeleton of what you need to prove convergence of gradient descent algorithms to barycenters in Wasserstein space, and maybe not necessarily just on the Bures-Wasserstein manifold. Right? And we call this an integrated PL inequality, where in this case, if I have a distribution over absolutely continuous measures, and I assume that elements of the support are absolutely continuous, say with respect to B, then I get this sort of inequality, this functional inequality, where I get sort of a constant factor times something that almost looks like the gradient squared at B, except I'm integrating this gradient squared sort of against S. And notice that this is in L2 of BS, but I really need this to be L2 of B. OK, so we can't actually make that work in general Wasserstein space, but we can make this integrated PL inequality give us a PL inequality in Bures-Wasserstein space. So let's take a geodesic from gamma sigma to the gamma that is sort of the normal distribution at the true barycenter. Right? I'm going to optimally couple these measures. Right? So x naught has distribution gamma sigma, 0 sigma, and x1 has distribution gamma 0 sigma bar. The integrated PL inequality I showed you, if we translate this to Wasserstein space, Bures-Wasserstein space, actually just you write it down and you immediately get this, where I've just plugged in the constant for my variance inequality, and I'm integrating against gamma s, against in L2 gamma s, where gamma s is this geodesic now. And really what this means, right, when I'm integrating, sort of taking this norm in L2, is really I'm taking the expected value of this sort of applied to some random variable xs. And here I'm using Cauchy-Schwarz to actually move this square inside. OK, so this is where we're at. We're at this, and we want to get to a PL inequality. So you plug in the form of the gradient. OK, you can basically write down the optimal coupling, right? The displacement interpolation. So I told you that if x0 and x1 are optimally coupled, then the sort of displacement interpolation between them is 1 minus s x0 plus sx1, right? And we're applying the sort of gradient to this. You do like a Jensen inequality. You do some sort of inequalities involving, you basically just have to, right, so this is Jensen's. Here, we need to translate this x1 back to x0, because again, we want this thing to be the norm with respect to L2 of sort of L2 of the law of x0. And so we can translate it back by just using these bounds. You combine the terms, and you're left with the final thing that you want, which is the norm of the gradient squared, which after plugging back in, right, completes the proof. Right? So basically what I've shown is that the difference in function values is bounded above by sort of 2 over zeta squared times the gradient norm in L2 of gamma sigma. OK, so I've given the results for Bures-Wasserstein space. And these things actually do show up when you code it up. Right? So we see a parametric rate for SGD. And in this plot, I'm actually showing you I fit a line to the log plot to actually show you the slope is -1. Right? And we get linear convergence of gradient descent. And just to finish with something interesting is when you start to make the distributions more ill-conditioned, if we use some form of averaging gradient descent, then we actually get much better convergence for the averaged algorithms than for just vanilla stochastic gradient descent. And this is something that you see sort of in the optimization literature, is that the averaged gradient methods achieve the optimal rate. But the previous results for the averaging sort of stochastic gradient descent algorithms on manifolds require things like strong convexity of the distance function, which we don't actually have here. And so it'd be interesting to actually think about how can we, do we actually get the optimal rate here with average stochastic gradient descent, which I conjecture we do, based on some sort of similar works in non-convex optimization with KL or PL inequalities. So to conclude, I've showed you basically that we can get linear convergence of gradient descent on the Bures-Wasserstein manifold. We also get a parametric rate for stochastic gradient descent. And both of these are in sort of a non-convex setting, right? This is non-convex really due to the non-negative curvature of this manifold we're dealing with. The further questions we have from this work are things like, can we actually show this integrated PL inequality holds in some more general case on Wasserstein space? And if so, then you actually get convergence of gradient descent and stochastic gradient descent in more general Wasserstein space. And the other question would be maybe averaging of stochastic gradient descent, right? Can we prove that this achieves an optimal rate? And if you're curious, you can check out our preprint on arXiv. Thank you very much.